Computers interpret digital photographs as dense, two-dimensional grids of raw pixel intensities. To identify the subject of an image, the machine must perform a series of mathematical operations to analyze this matrix. If we feed this visual data into a standard feed-forward neural network, we encounter an immediate structural barrier. These networks require a single one-dimensional vector input. To process a 64 by 64 image, we unroll the grid into a flat line. This flattening process destroys the topological integrity of the data. Pixels that were physically adjacent and structurally related in two-dimensional space are suddenly mathematically isolated, leaving the network without the spatial context required to make sense of the image. To accurately process visual data, we need a mathematical countermeasure, an architecture that can ingest and evaluate information as an intact volumetric grid. This schematic maps out the convolutional neural network, built exclusively to preserve and analyze spatial relationships. By tracking a data matrix as it flows from left to right, we observe the specific interleaving phases of feature extraction before any final classification. This architectural shift allows the system to analyze the data's geometry in its raw volumetric form. It creates a pipeline where the network can isolate specific spatial patterns before any data is lost to flattening. This process begins with the convolution layer. Rather than analyzing the entire image globally, this layer acts as a localized feature extractor. We achieve this using a small weight matrix called a filter. Hovering over the top left, it focuses on its local receptive field. It slides sequentially across the input, multiplying its weights by pixel values to generate a new numerical feature map. During this scan, the network relies on parameter sharing. The exact same filter weights are used to evaluate every single location across the entire image. In the earliest layers of the network, these filters are highly specialized. They search for basic structural elements, like distinct edges, like sharp corners, and local textures. Because the weights are shared, computational overhead drops drastically. More importantly, it grants the network the ability to detect a specific structural feature, regardless of where it appears in the frame. The mechanics of this scan are highly configurable. The step size the filter takes across the matrix is known as the stride. If we increase stride to 2, the filter jumps 2 pixels, yielding a smaller output grid. This exposes a flaw. Borders shrink, and outer edges are undersampled. To correct this, same padding adds an artificial border of zero-value pixels around the matrix. With this adjustment, the math aligns perfectly. If we take a 64 by 64 input, apply a stride of 2, and same padding, the output feature map reduces neatly to an exact 32 by 32 grid. Stride and padding are precise architectural tools. They give engineers exact mathematical control over the spatial volume of the data, layer by layer. At this stage, the output of the convolutional filter is strictly linear. However, simple linear math is insufficient for modeling complex, irregular patterns found in the real world. We inject nonlinearity through the ReLU activation function. Its graph outputs 0 for negative inputs and leaves positive values mathematically unchanged. Applied to an array, it acts as a strict threshold, immediately clamping every negative number down to 0. Unlike older activation functions that saturate and slow down training, ReLU's constant slope for positive values ensures the network can learn quickly. It prevents the mathematical signals from shrinking toward 0 as they pass through deep layers. But there is a systemic risk, known as the dying ReLU problem. If too many neurons are forced to 0, they can become permanently inactive during backpropagation and stop learning entirely. Despite the risk, ReLU is highly effective. It acts as a biological threshold, allowing only mathematically strong features to pass forward, while it ruthlessly suppresses all background noise. As the network progresses, it uses dozens of distinct filters, stacking multiple feature maps together. The depth of the data expands rapidly, threatening to explode the computational load. We manage this expansion using a pooling layer. Looking at this 2x2 grid, a max pooling operation aggressively downsamples the data by selecting only the single highest value, in this case the 9, and discarding the rest. While an average pooling method would calculate the mean of the 4 numbers, max pooling is generally preferred because it isolates the most dominant signal, helping to preserve the distinct feature edges. Structurally, a pooling layer is unique because it contains zero learnable parameters. It is a fixed, deterministic mathematical operation. By condensing the data, pooling also creates translation invariance. It ensures the network will still recognize a specific feature, even if its exact pixel coordinates shift slightly in the original image. This forms the core interleaving loop of the architecture. Convolution extracts the signal, ReLU activates the nonlinearity, and pooling condenses the footprint. Through repeated cycles, the network systematically trades raw spatial resolution for dense semantic meaning. Deep inside the network, the data matrices no longer resemble a physical photograph. Instead, they are dense blocks of high-level semantic concepts, holding abstract representations of shapes like an eye or a wheel. Because the original spatial geometry is no longer relevant at this extreme depth, the architecture must transition formats to reach a final decision. The structural bridge between feature extraction and classification is the flattened layer. Here, the multidimensional tensor is mechanically unrolled, rearranging the remaining semantic data into a single, massive, one-dimensional array. The flattened layer is a necessary compromise, safely translating the refined spatial features into a linear format that traditional classification algorithms can actually process. That linear array flows directly into the fully connected, or FC layer, where every flattened node connects to every single output node. The FC layer serves as the final judge. It mathematically weighs all the extracted abstract features against one another to make a holistic prediction about the entire image. However, there is one final mathematical hurdle. The raw numeric outputs generated by the FC layer, known as logits, are arbitrary, unbounded integers. To make these numbers legible, we pass them through a softmax layer. This chart illustrates how softmax normalizes those arbitrary outputs, transforming them into a clean probability distribution where the total sum equals exactly 100%. The convolutional neural network represents a triumph of matching architecture to data topology. By respecting the inherent geometry of spatial data at the input, it successfully compresses millions of chaotic pixels into highly confident, mathematically rigorous truths at the output.